and I will show some video clips of our dances, but I just hate showing video of dances that are designed not to be shown on video, but are designed to be performed live. But in order to give you a sense of what we do, I have to show clips. And I brought the props because I think there's something about the physicality and the weight and so forth of props that just gives you a better sense of what you have to do with them. We have a variety of ways in our dance company that we approach linking dance and mathematics. Sometimes we'll take a math idea and put it on bodies moving in space, in the studio, on stage, see what happens, see what we can do. Sometimes we'll look at dances, could be dances we or other people have choreographed, and look for the mathematical ideas that are already embedded in, often in the choreographic process. But as this inversion, I hope, demonstrates, which reads dance one way and math the other way, what we do mostly is try to find ways to play with dance and math in situations where you can't really pull one apart from the other. They're so that we find they're so connected that we don't really want one to take over the other. Let's see. Here. These are the main people who started this. That's Eric Stern over there on your right, and me on the left, and Scott Kim, a puzzle designer who worked with us in the 1990s. And actually, that's us when we could jump that high. I certainly can't do it anymore. That's where you can find us, mathdance.org. And I thought what I would do today is try to share with you a variety of ways in which we have found to connect math and dance. Now, the way most people might expect we would do this, and a lot of people do this, is take some mathematical theorem and translate it to moving bodies. And I will show you one example of that. And as I said before, sometimes we look at dance itself and find what kinds of mathematical ideas we find in dance. And of course, we put them together and play with them. That, like I said, that's really mostly what we do. But sometimes I found dance can inspire or suggest new math problems to work on. And to work on as more like as a traditional mathematician might work on them. I'll show you an example of that. Many of the shows that I've done in the last 10 years have used the math and dance connection as a kind of part of the palette of paint with which I or we create choreographically. In other words, the math and dance connection is not the end in itself, but just part of the process or with which we do other things. And one of the recent shows that we're still performing a good bit is called The Daughters of Hypatia, which is about the stories of celebrated important women mathematicians throughout history, and also about the work that they've done and the struggles they went through, and up to contemporary times. And we use various mathematical math-dance elements in doing that storytelling. And in general, for me, part of or a major part of what I'm interested in presenting choreographically or on stage has to do with issues of equity, issues of social justice, and so forth. Another recent show is called Mosaic, which is about Palestine, Israel, and issues of justice and war and peace there. And we've also had a huge development of classroom activities that have grown out of the work on stage. How can we translate some of this to the stage? And there are movement games that we can play. I don't know if we'll get to that. That's what the hats were for. Okay, so here's an example of what we tend not to do very much, which is take some mathematical theorem and translate it to the stage. But I did do it after working on this kind of thing for about 20 years. I thought, well, what could we do? Is there a theorem we could present? Two squares, can you find another square that has the same area as the sum of those two squares? Well, there's the Pythagorean theorem. If you place them on the sides of a right triangle, you see that's really what we're dealing with. If you take the two smaller squares and create a tessellation, then you can create a proof. It's called Perigle's proof from the 1800s, which is based on this tessellation. It's actually very similar to a proof from about 1,000 years ago by an Islamic mathematician. What we do is take the purple square, which is the sum of the two smaller, it has the area of the sum of the two smaller ones, and overlay a tessellation on the tessellation of the green and yellow squares. And then you can see that the larger square is composed of the smaller square and these four quadrilaterals that fit together to make the other square. So that's a visual proof, which are visual proofs becoming popular these days, of the Pythagorean theorem. And here's a little excerpt. Again, I just hate showing video of dance, but here it is, of a piece. This was done at the Jurassic Project. Let's see if, whoops, let me put this on so you can hear the music. Oh, sorry. So we're using these foam core pieces to essentially show that dissection that creates the proof. The music is by a group called Zambra, a women's choral group that I've done a lot of work with in Santa Cruz. And they created a song based on the Pythagorean theorem for a show we did with Keith Beverly. Yeah, so there's the dissection. Okay, so here's another direction in which we can connect math and dance. This is something I grabbed from the web.
The men pass right in the middle, left on the outside.
It's called a Hey for Four dancers, found in Scottish country dance, for example.
We are going to go
You can see them circling
times
in a fairly complicated way.
As you notice, they always pass right in the middle. At the end, we will do a balance and...
So what kind of math is there? Well, found in Contra Dance, but also in English and Scottish country dance. Partway through, or the first thing you see is that four dancers line up, A, B, C, D. And the next way they line up, B and C have changed places. They're not quite horizontal, but dancers do form somewhat of a line. And by the way, this is similar to something that was discovered in the late 1990s and has also been the subject of recent research, which is that it is conceivable that four equal mass bodies operating only under the influence of gravity could circle each other in this pattern somewhere in the universe without banging into each other in a repetitive pattern. And there are a lot of physicists and mathematicians working on this who found some beautiful, what they call n-body choreographies.
That's gravitationally stable?
This one has not been proved to be gravitationally stable, but it's thought to be. So people are still working on this. There really is only figure 8 with 3 bodies that has been proved to be stable. One of the people who worked on this, Richard Montgomery, who's at UC Santa Cruz, actually. Anyway, it's a subject of contemporary research, and there's some beautiful symmetric patterns of multiple bodies that people have found. Anyway, it's also a contra dance form, and what you find in this particular sequence is you find 8 of the 24 permutations of 4 dancers in a row, and ABCD is the first one that lines up, then the middle 2 switch, then these 2 switch, so they switch and they switch, and then the middle switches, AD to DA, and then these 2 people switch, and then the middle switch, then they'll switch. So it's a pattern that is formed here, and you can see where A is going and where B is going. B is doing exactly the same thing that A does, but a beat later.
I didn't know you could get all 4 with a double switch.
You can get all 24.
Yeah, I mean all possible.
Yes, you
With
can.
a double switch, I didn't know.
Yeah, and this is something that was discovered several hundred years ago, not by mathematicians, but by people who did what's called change ringing, which are where people just permute the sequence of bells. And these bells are extremely heavy, some weigh a couple of tons. And so if you ring one, you have to wait a few seconds or a part of a second before you can ring it again. And so if you have this bell, then a third, then a fourth, you can't ring this one and then immediately ring it again. So you can only switch the order of 2 that are played next to each other.
So it's the same pattern.
Yeah, and so people discovered ways of going through, say, all 24 permutations of 4. Now you saw the dancers actually did 8 of the 24 permutations. But here are all 24 permutations, and 2 of these are neighbors in this graph if you have switched either, in this case, the first 2 have switched. You can only switch neighbors. Again, you can't go from 1, 2, 3, 4 to 2, 3, 4, 1, or 2, 3, 4, 1 to 1, 2, 3, 4, because then you'd be playing 1 right after itself. You can only switch neighbors. And this forms what's called, this graph forms what's called a permutahedron, which actually is a truncated octahedron, so it has an interesting 3-dimensional shape.
Is that flattened out?
Yeah, this one is flattened,
Okay.
and here it is as 3-dimensional.
Well, it's not really truncated, it's actually flattened.
Well, if you take an octahedron and chop off the vertices, it'll look like this thing. This 24 point, it's 24 vertices. Anyway, so there is that mathematics that is connected to that dance form, the Hey for 4. If you do double swaps, so in the dance, 2 people swapped at the same time, 2, 3, 1, 4, 3 and 2 switch places, and 4 and 1 switch places, then we add these purple lines to the configuration. And this purple sequence you might think of as the sequence that the 4 dancers did. So there's some beautiful mathematics that connects to that that sequence in that dance. Now, interestingly, the Contra Dance, or Scottish country dance, English country dance, where that Hey for 4 was developed, was developed around the same time in England or Great Britain that people were discovering the patterns in change ringing. Though I haven't seen any historical reference that says the mathematicians and the musicians were working with. No, the dancers and the musicians were working with each other.
And change ranking?
Change ringing is this sequence of bell.
Oh, yeah.
Yes. Yeah, in one of those pictures I showed you before, there's the National Cathedral in D.C. The other, there aren't a lot of places in the U.S. where you can find change ringing done, but in D.C. there are 2 places. The other place is the old post office building, which is now called the Trump Tower. That's the other place in Washington, D.C. that has these bells.
And they still have it there?
I don't know what's happened. I'm afraid to find out.
Hell's bells.
Yeah. Anyway, here's another cycle through the permutations.
Oh my God.
And this is called a Hamiltonian cycle because it goes to each of these vertices exactly once. So there's some more mathematics there. And what I want to show you is a dance sequence where we played with it. So the idea wasn't to let the audience know what this mathematics was, but like I said, to just play with it. The dance is called Switch, and the dancers are speaking about genetic sequencing and what kinds of, it's a kind of humorous dialogue or quadrilogue, because there are 4 people in it, in which the dancers go through this sequence and go to each The dancers are standing in a line, and we go through every one of the 24 permutations in a line. But that isn't apparent to the audience. What we're actually doing is presenting something that is about how things might switch, how DNA, parts of DNA can switch with each other in actual DNA chains. Anyway, here's this switch from 2000.
How often do these things happen?
Don't people have DNA?
Is switching people like switching DNA?
Is switching DNA like switching people?
Is combining the efforts of two people like combining DNA?
Sometimes.
I'm an identical twin, but is my DNA identical to my sister's?
Then what about me and my brother? Don't we have similar DNA?
What about me and bacteria?
Can they switch?
When virus DNA mutates, does it always get more dangerous?
Do mutations make monsters? Do mutations make angels? Or do people become monsters or angels all on their own? Don't you mean our own? What about twins? If my sister has children, does that like me having children? Has your DNA changed since you were born?
Is it changing now?
If my DNA changes, are you still you?
And what about her?
Am I still me?
So actually,
My identical.
the dancer on the left is an identical twin, and so some of the stories we tell in this were actually based on things that she and her sister did, trying to fool people and so forth. I think we're not going to have time for this, but this is, we could have an example. Well, why don't we do it, because we might as well do some audience interaction. So here are 1/4 of the permutahedron, and a tap is a tap on the head, a clap is a clap. This is a slap, and this is a snap. So I'm going to get you to practice 1/4 of the permutahedron with me. And so let's just do the first one very slowly. Tap, tap, slap, snap. So we're going to go on, and here we go. Tap, slap, clap, snap. Tap, slap, snap, tap, snap, snap, tap, snap, tap, slap, tap, snap. That was perfect. I tried to make a dance where I did all 24, and I could never get through it, so I didn't perform. And not these things, but 24. I put 4 movements together and tried to get through all 24, and I worked on it for like 3 or 4 weeks, and thought, no, can't do it. Anyway, I think we're getting close to my time. I can show you a little bit more here. This is one of the props we've worked with, and dancers tend to call these 2Zs or 3Zs. So this is a 3Z, 3 PVC pipe sections, and again, it's just more meaningful, I think, to see it in real life. This is an example of how dance led to a new math problem. We made some sequences for these. In performance, you have the problem, well, how do you hold the thing? How do you manipulate it? And of course, what happens in rehearsal, you don't want to make a noise like I just did, things fall. People bang into each other. It's a mess. And so the performance problems are essentially, how can you do something interesting without making a mess? The dance problems are, well, what movement qualities are there? What does the audience see? What are you actually trying to say with your dance? But they are mathematical problems. Well, what shapes can we do? What are the sequences of shapes? How do we find interesting transitions between them? So here are, I guess I get to show a little bit of 2 pieces, Pipe Dreams and Shadowed Flight. Let's see. I think you can see that. So we made an octahedron. and a cube. And all the dancers have a 3Z essentially, so there are 4 times 3 or 12 edges that we're using to create these things.
Oh,
And they're painted with glow-in-the-dark paint. We use black light. But we also use some rowing motions. We're trying to use a variety of ways of playing with these things. This is a piece called Shadow Flight. It's not actually videoed in slow motion. We're manipulating them at that speed. This is the one where we drop the things in rehearsal all the time because you're having to hold parts of 2 of them at the same time. And this actually folds very briefly into a tetrahedron. Okay, yeah, there it is. So the math problem was, well, what kinds of shit, am I done? Okay, I'll say what the math problem is and then I'll stop. The math problem is what kind of shapes can you make with, say, PVC pipe sections? Is there a way to make the Platonic solids, for example, all of them? And is there a shape that will make all the edges of all 5 Platonic solids? And it would have to have 6 edges because the numbers of edges of all the Platonic solids are all divisible by 6. And these are the possibilities, these trees, and it turns out that only one of them works. The others won't make all of them. And I have these names. The one that works is this one. And the proof actually took a number of pages and was kind of tedious, but here they are created. So that one folds into tetrahedron, cube, octahedron, and you can see that one person holding a blue 3Z and another holding a red 3Z together make that tree that I showed you, and could make the, in a very symmetric way, make the icosahedron or the dodecahedron. Anyway, I think that's about all I have time for. I will show you one of the, kind of connects to what Evie was doing with LED lights, because we've been playing with, we also I go to the stores and find new objects and try to figure out what we could do with them. So I found these in Walmart. They're pool balls. People put them in their pools and they stop working according to the reviews after about 30 seconds. But we have dancers manipulate them in the dark and make interesting patterns. So this is one of the latest things that we played with at the Jurassic. Okay.